Hello everyone, welcome to the course on Introduction to Multi-Agent Systems. In today's lecture, we'll talk about the basics of graph theory. So let's get started with a practical example. What we see in the figure is the city of Königsberg. Now the city of Königsberg has the river Pregel or had the river Pregel flowing through it. The river flew in such a manner that the city actually got divided into 4 parts. So this is the first part. B and C are the major land masses in the city, and A and D are the islands in the city. And what we see here are 7 bridges which basically connect these land masses. Now in the year around 1736, mathematician Carl Gottlieb Euler posed this question to Leonhard Euler. So back in the day, Euler was actually a mayor of a city nearby. So he posed this question to Euler, asking him if it is possible to do a round trip over the entire city such that every bridge is crossed only once. So Euler tried a lot to come up with a solution on how one could actually create a walk across the entire city, a closed tour, so that every bridge in the process gets covered only once. Let's see an example of what a walk or a tour here would look like. So suppose we start at this point, then as soon as this point is reached, in order to be able to cover or go over this bridge, one has to go over any of the other bridges which have already been traversed. So now I'd request the students to pause the video right here and see if they can actually create a walk which can do that. So you can keep trying for a long time, but it is guaranteed that you cannot find a solution, because in fact the solution to this problem does not exist. There does not exist such a path which can actually go around the entire city along a closed walk in which the bridges are covered only once. And while attempting to actually find a solution to this problem, Euler started the field of graph theory. So now let us try to frame this problem in a graph theoretic manner. In order to do that, we denote the land masses and the islands as points, and every bridge that we see is actually denoted as an edge connecting the 2 land masses or the islands. So let's see what it will look like. It looks like this. We have 4 points here. So these points actually referred to as vertices. We have 4 vertices here corresponding to the 4 land masses and islands, and we have 7 edges. The 7 edges are simply the bridges of Königsberg. Now, in a graph theoretic sense, this problem becomes a traversal problem where we are trying to traverse all the edges of this graph such that every bridge is traversed only once. And we already know the answer to this question is no. Now, by representing the entire city and the corresponding pathways in the form of a graph, Euler made it a very simple process of visualizing whether paths are possible or not. Meaning, graph theory can serve as a very useful tool in solving several real-world problems. Now let us see how can we actually define these graphs. So let's start by defining what is a finite graph. A finite graph is simply a finite, let's start by defining an undirected graph. A finite, undirected and simple graph is built upon 2 things. The first one is the set of vertices denoted as V, and the second one is the set of edges denoted as E. Now, any graph is actually denoted in this manner. in terms of both the set of vertices and the set of edges. Now note that in general, any finite graph, so the word finite actually stems from the fact that the number of vertices and edges that we have here are actually finite in number. Now note that while we have defined this for a finite graph, an undirected graph, a graph in general can be both directed or undirected. When is a graph undirected? When the edges associated with the graph do not have any direction sense to it, and it is directed when the edge is actually directional in nature. So we talked about it in one of our earlier lectures. In an undirected graph, an edge would look simply like this, whereas in a directed graph, we would have to mark an orientation. Let us now see some real world examples of graphs. So the first image is that of the Delhi Metro, and we see that there are several nodes and edges which are connecting the different nodes. Similarly, the second image is that of the flights that exist between New Delhi to San Francisco. So we see here that there are several nodes which have been marked. Each node actually corresponds to one of the airports, and sometimes there are direct flights, which would mean just a simple direct edge between the 2 points, and in some cases there are no direct flights and people have to go to a different city and then take a flight from there, something like this. And the third image is that of the spread of COVID-19. Now in general, graphs can also be used to model different behaviors. So the graph that we see here is actually connected from the global tourism network, which shows as people traveled across the world, how COVID-19 spread into the world. Now, graphs can be used to solve several real-world problems, as we saw earlier, like creating walks around it. And these walks are governed by simple features like the edges and vertices in the graph. So let us try to see some of properties that we can derive from a graph structure. So let us say we have an undirected graph G consisting of a vertex set V and an edge set E. Now, any two vertices Vi and Vj are said to be adjacent if the edge denoted in this manner belongs to the edge set. So meaning, if we take an edge and the two vertices at the end of this edge are actually adjacent to each other, said to be adjacent to each other. Now, using adjacency, we can define the notion of a neighbor of a graph. Let's see how it goes. Now, the set of neighbors n of a vertex is simply the set of all vertices that are adjacent to it. Let us see an example. In the example of the Königsberg Bridge problem, so this is the original map and the corresponding graph structure looks like this. Now, we see here that the vertex A actually shares an edge with C, B and D, meaning A is adjacent to all three of them, B, C and D. In other words, A in fact has 3 neighbors. Now, if we look at the node B, B now on the other hand is connected only to D and A. So, unlike A, B has only 2 neighbors, A and D. Now, the example that we talked about before was undirected. However, in real world networks, like we discussed before, in robotic networks, when robots have limited field of view, in those cases the graphs can actually become the edges in the graph can actually become directional, leading to directed graphs, also known as digraphs. Now, in a digraph G, suppose we are given an edge Vi Vj belonging to the edge set, then Vi here is simply known as the in neighbor of Vj. So, let us denote the graph here, edge here. Vi is the in neighbor of Vj, while Vj becomes the out neighbor of Vi. This simply follows from the direction of the edge. since the edge coming from Vi is incoming to Vj, it is known as an in neighbor. Similarly, now since the edge is going out of Vi towards Vj, Vj is known as an out neighbor. Ni denotes, in a similar sense as we did for the undirected networks, Ni of Vi simply denotes the set of all in neighbors of Vi, and N out of Vj simply denotes the set of all out neighbors of Vj. Let us quickly see an example. So, for the graph that we see here, if we look at the node Vi, V1, now who are the incoming neighbors, or what are the incoming edges? The first one is this, the second is this, meaning it has two neighbors V2 and V4. Now, similarly, again let us try to find out the out neighbors of V1. So, it has only one outgoing edges which goes to V2, meaning its out neighbor is simply V2. Okay. Now, the edges in the network can actually be used to create walks and graphs. So, let us see what is a walk and how can we create walks in a network. Now, a walk is simply a sequence of vertices and edges which always start and end at vertices. And so, the rule is when we are constructing between any two vertices, there always has to be an edge. Let us see in this example what a walk will look like. Now, for the given graph here, the walk is denoted as gamma 1, and let us try to trace it. It starts at node 1, goes along the edge E1. So, there is a typo here. It should be E1, goes to node 2, E2, then 3, E4 to 4, then E6 to 5, then again E5 to 4. Okay, there should be another E4 here, back to E4, from 3 to E3 and back to 1. So, the walk that we drawn here looks like this. So, this is an example of a walk. Now, very similar to the notion of a walk is a trail. What is a trail? A trail is simply a walk with no repeated edges. So, let us see again an example of this. So, this is the same walk that we discussed before. Let me quickly trace this. If we see here, the edge E4 is actually repeated twice in the graph, meaning this is not a trail, this particular walk. Let us look at gamma 2. So, gamma 2, let us try to draw gamma 2. So, all of this should be E1 to 2 to E2 to 3, to 4, then E6 again to 5, and then E5 to 4. It stops right here. So, we see that the walk that we have created here does not have any edge repeated, meaning this is a valid trail. Again, similar to the notion of a walk and a trail, we have something that is known as a path. So, what is a path? A path is actually a walk with no repeated edges. Let me pose a question here. So, before that, just make sure that we take a note of it. It is allowed for the first and the last vertices to actually be the same, in which case it is known as a closed path or a cycle. However, the vertices in between cannot be the same, also known as the inner vertices. So, let me pose a question here. The question is, can we design a walk which is actually a trail but not a path? This is the first question. And the second question is similar to this. So, I will urge the students to pause the video here and think for a few minutes. Now, the answer to this is yes. We can easily generate trails which are walks which are actually trails but not really paths. We will quickly see an example for it. But there cannot exist a walk which is actually a path but not a trail. So, the proof of this is very straightforward. You are all encouraged to try the proof of this. Let us quickly see an example. So, let me draw the previous walk that we had or previous trail that we had. If we look at this walk, we see that node 4 is actually repeated twice, the vertex 4, meaning it is not a path. Whereas, let us look at the second one. It goes like this. E4 to 4, then 4 to E6 and E6 to 5, which just stops here. So, we see that in this process none of the vertices are actually repeated, meaning it is a path. Okay, now using the notions of walks in a graph, we can talk about the notion of connectivity within graphs. So, let us see what that looks like. Let us consider an undirected graph. Now, in general, in an undirected graph or an undirected graph is said to be connected if and only if there exists a path between every pair of vertices, meaning if we start from any vertex, we can actually reach any other vertex. Similarly, if every vertex cannot be reached from every other vertex, the graph becomes a disconnected graph. Let us quickly see examples for it. So, the first figure we see here, if we start from any point, we can always create a walk which can take us to every other point. Hence, the graph is connected. But if you look at the second figure here, we see that we can never construct a walk from V2 which can actually bring us to V3 or V4, meaning the graph here is actually disconnected. Let us now look at directed graphs or digraphs. Now, similarly here, a digraph is said to be strongly connected if and only if for every pair of vertices u and v, there exists a directed path from u to v and similarly from v to u. Now, a digraph is said to be weakly connected if its underlying unconnected graph is connected and it is not strongly connected. Let us see examples for it. So, if we look at the first digraph here, if we start at V1, we can reach every other vertex from here. Similarly, if we start from here, we can trace a similar walk and reach every other vertex. If we look at the second graph here, if we start from V4, now there does not exist a walk which can bring us to V3, meaning the graph is not strongly connected. However, if we remove the direction of all the edges, then we can see that the graph is actually connected. Such a graph or digraph is known as weakly connected digraph. So, let us now come back to the Königsberg bridge problem and try to see or try to frame this problem now in terms of the notations and terminologies that we just learned. So, again the problem says, can we have closed tours across the city of Königsberg such that every bridge is traversed exactly once? And what do we have? Now, we can easily see that if I start from A, I can reach every other vertex in the graph. Similarly, from D and B and C as well, meaning the graph is connected. However, how much ever we try, we know this from before, that desired closed tours cannot exist. Now, closed tours in this case simply refers to a closed walk or a closed trail, since in a trail none of the edges are repeated, and this is exactly what is said. So, the requirement is to construct a closed trail in which every edge is traversed at least once. Since this is an unsolvable problem, now is there a way to add an edge in the network such that the problem now becomes solvable? So, I'll end the lecture with this question and request the students to think about an answer for this. So, we have the Königsberg city. The problem at hand is to construct another bridge in the city so that we can start making closed tours such that all of the bridges are covered, but none of the bridges are actually repeated. So, with this, I'll pause the lecture here. Thank you and see you next time.